Hello everyone, my name is Fridman and I'm a PhD student in Ben-Gurion University. Today we will talk about HPC checkpoint restart strategy using NVRAM. So we know that HPC systems are a critical resource for scientific research and advanced industries. Therefore, we see more giant supercomputers built, and today we meet the exascale era in which supercomputers provide more than 1 trillion floating point operations per second. However, as these supercomputers become larger with many more components and compute nodes, they tend to experience frequent faults. And this is one of the major challenges of exascale computing. Checkpoint restart is one of the general mechanisms for fault tolerance of scientific computations. Specifically, in transparent checkpoint restart, the state of the program is saved without any knowledge of the application or intervention from the programmer. An example for a library that supports transparent checkpoint restart is the distributed multi-threaded checkpointing, DMTCP. In explicit checkpoint restart, on the other side, the programmer has to persist variables manually and must store the whole required computational state to be able to recover from a valid state. An example for explicit checkpoint restart library is the scalable checkpoint restart, which enables asynchronous data transfers to the parallel file system. However, in both methods of checkpoint restart, checkpointing to standard storage devices like SSDs or HDDs usually creates huge time overheads. Non-volatile RAM technologies aim to feed the gap between DRAM and storage, creating a new tier between the standard storage devices and the volatile memory hardware. They're byte-addressable like DRAM, but the data stored on the NVRAM can be retained whenever the system is shut down or loses power. And usually they come in vastly larger capacities than DRAM. Persistent memory aims to have memory-like performances, but there is still a certain gap. Last year, we presented at the FTXS workshop the capabilities of NVRAM in certain use cases for HPC computations. We focused on persistent memory file systems as fast storage for diagnostics and for checkpoints of scientific applications. We also presented an example of the BT solver, one of the main solvers in linear systems. We applied DMTCP for the transparent checkpoint restart and the scalable checkpoint restart library to persist the state variables of the solver in the explicit case. As we expect, the transparent checkpoint restart carries a certain memory overhead, so we get smaller checkpoints with the scalable checkpoint restart library. In both methods, checkpointing to NVRAM brings better results in time overheads rather than writing to an SSD device. We expand this work and now present how NVRAM can be accessed directly in algorithm-based fault tolerance techniques. These techniques are tailor-made to specific applications to support fault tolerance without the need of full checkpointing. NVRAM can be accessed directly from the application and not necessarily via file systems, completing the use cases image of NVRAM for recoverability. So how does it work? Two possible NVRAM cluster architectures can be relevant in our day's systems. In the homogeneous NVRAM cluster, each compute node is equipped with its own node NVRAM cards connected directly to the CPU bus. This architecture is relevant, for example, in cloud HPC computing, when the goal is to equip each compute node with as much as compute and memory resources as possible. In this architecture, NVRAM can be accessed via the PMDK library by creating persistent memory objects directly on byte-addressable NVRAM. The second architecture holds the NVRAM on a remote subcluster on dedicated nodes. This architecture is relevant, for example, in Aurora, when the DAO storage system is planned to consist NVRAM outside the compute nodes. In this architecture, we use an extension of the one-sided communication in MPI that enables direct access over RDMA to remote MPI windows on byte-addressable NVRAM. For conclusion, NVRAM can enhance dramatically fault tolerance performances of scientific applications, and we hope that NVRAM technologies would continue to develop, even though Intel just announced the death of Optane, one of the main products of NVRAM. So we still believe NVRAM has great potential in closing the gaps in HPC, and we will be very happy to hear more about it. Thank you.